Okay, so let's quickly go through both the integrating factor method and undetermined coefficient method to solve this, get these answers as quick as possible. Hopefully it came back to you by quickly reviewing. Then we'll talk about how to use the Laplace transform to solve this. With the integrating factor method, we need to find an integrating factor, typically called mu. It's a function of t. It's e to the integral of whatever expression is in front of the y there when you write the differential equation in this form. It's a constant function there, just 4, but it doesn't have to be a constant function. Of course, it's easier when it's constant, but the integrating factor method works even if that's not a constant function, and that's an example of something that you should look up and practice before the final exam, including the case where it's not a constant. But this case, it's a constant, just 4. So our integrating factor ends up being e to the 4t. You multiply both sides of the differential equation by the integrating factor. I'll just write y prime. Don't forget to do it to the right side too. That's the most common mistake, is to forget to multiply it on the right side as well. E to the negative 5t times e to the positive 4t will be e to the negative t. So by multiplying both sides of the differential equation by the integrating factor, you have made it a factor of both sides of the equation. That's why it's a factor. And it's an integrating factor because the left-hand side, almost as if by magic, becomes easy to integrate, because by the product rule, it's the derivative of the integrating factor times the unknown function y. And it is a y of t. You could put a t in there if you like. Right? Double check that in your mind. It is the derivative of this. If you differentiate this with the product rule, e to the 4t is the first function. So there's the first function times the derivative of the second function plus the first function y, e to the 4t, excuse me, e to the 4t times y prime plus y, the second function, times the derivative of e to the 4t, which is 4e to the 4t. Because it's the derivative of that, it's easy to integrate. Now you integrate both sides. You don't have to bother writing an integral symbol. Integrating a derivative gives you the function itself. You do have to integrate that on the right side to get negative e to the negative t. Don't forget your integration constant plus c. Solve for y. Multiply both sides by e to the negative 4t so that y is isolated on the left. This times e to the negative 4t will be negative e to the negative 5t. C times e to the negative 4t is exactly what I said. Now use the initial condition. 3 is y of 0. Plug in 0, get negative 1 plus c. So c is 4. And your unique solution, if I have not made a mistake, is y equals e to the negative 5t plus 4 e to the negative 4t. Like, look good to people? Did you get that? All right. So that's a quick review of the integrating factor method. Again, you should, before the exam, final exam next week, try it for examples where that's not a constant function. It still can be done, at least if the integrals are doable. Undetermined coefficient method is where you consider the associated homogeneous equation y prime plus 4y equals 0. Make the right-hand side 0. It's not the same differential equation. That's a different differential equation. But its general solution is related to the general solution of our original equation. That's what the theory about the linear equations is all about. And its general solution can be found, well, yeah, you could separate variables, but this is our easiest kind of differential equation. We can just guess. Arbitrary constant times e to the negative 4t. Which of course then matches what you see right there with the integrating factor method. And then to find this part of the general solution of the original equation, you need to guess. Go back to the original equation and make an educated guess as to a particular solution. Right? The right-hand side is e to the negative 5t. It wouldn't make any sense to guess cosine of something or sine of something or even t squared or t cubed or some linear combination of those. It only makes sense to guess something times e to the negative 5t. a times e to the negative 5t, where a is going to be an undetermined coefficient that we've got to find. C is arbitrary, but a is something particular. A has to be some particular number. Find yp prime. Plug these things into the left-hand side of the differential equation. Get negative 5a e to the negative 5t plus 4a e to the negative 5t. We're setting that equal to the right-hand side function, e to the negative 5t. This simplifies to negative a e to the negative 5t. So the only way these two functions are going to be equal for all values of t is if a is negative 1. This implies a is negative 1, which then brings you back to the same thing we got up there. And the same unique solution of the initial value problem. Thinking about our linear algebra abstract theory here just a little bit before we go on to Laplace transforms. Y prime plus 4y, that symbolic thing could be thought of as defining a linear transformation, more precisely a linear differential operator between function spaces. What function spaces? It's kind of up to you, to tell you the truth. The simplest function spaces to pick would be C1R to CR. CR represents the vector space of all real valued functions that are continuous on the entire real number line. Why the entire real number line? Because it just keeps it simple. I could pick an interval here if I want. C1 represents the space of all continuously differentiable functions defined over the entire real number line, meaning not only are they continuous, they have a derivative that's continuous everywhere. Why is this linear transformation from this space to this space? Well, it's just one example of something I can pick. But if you differentiate a function that's differentiable and get a continuous function, then you are going to be in this space. The output of this transformation, if the input is in here, will be in there. That's why this is kind of just the simplest thing to pick. These are both infinite dimensional vector spaces. They don't have finite bases. But certain subspaces are finite dimensional. And in particular, the solution space of the homogeneous equation is the kernel of the linear transformation. And it's, in fact, a one-dimensional subspace. It's all functions of that form. It's the span of e to the negative 4t. A one-dimensional subspace of this infinite dimensional space. E to the negative 4t forms a basis of the kernel of this linear transformation, which is the same as the solution set of this homogeneous equation. And then for the non-homogeneous equation, your solution space, so to speak, is the set of all functions like this, where C is arbitrary, which is not a subspace, because it doesn't go through the quote-unquote origin. Right? This goes to the origin of this vector space, quote-unquote origin, because it includes the zero function if C is 0. This one's not a subspace because it doesn't include the zero function. No choice of C will make this the zero function. So yeah, that's the solution space, so to speak, of this non-homogeneous equation, but it's not a subspace in the official sense of that. It's kind of like a shifted subspace, so to speak. It's, if you imagine by analogy, a line going through the origin in the plane being the null space of a matrix or the kernel of a linear transformation. If you shift it, you might get a solution set of a non-homogeneous system, but it no longer goes to the origin, so it's no longer a subspace. All right, just to remind you of some terminology here and some ideas. All right, main thing we want to do today, though, is talk about Laplace transforms. For this example. Laplace transforms is another method for solving this differential equation, and in fact, the initial value problem. So there we have it again. We'll see, we're about to do it. We'll see it's harder, especially since we're going to derive some things from scratch. It's a harder method. However, we're not doing it just for the sake of doing something that's harder. We're doing it because this method has benefits for other kinds of differential equations. In particular, second order equations, especially, where the right-hand side forcing function is actually discontinuous. Analogous to thinking about a model, maybe where you've got a mass and a spring going back and forth, and maybe you hit it with a hammer. Impulse forcing, it's called. Maybe just once, or maybe you hit it with a hammer periodically. The Laplace transform is much better at handling a situation like that than these other methods. Okay, so you got to keep that in mind. It's meant for other purposes, discontinuous forcing functions in particular. All right, but we can apply it to simpler examples, though we will see the method is harder. But we got to know what the Laplace transform is in the first place. The Laplace transform, cursive L, is a linear transformation. Hey, linear algebra relationship between function spaces. It takes a function of t as input, call it little y of t, and gives you a function of s as output. What's s? It's just another letter. Want to pick a different letter. So traditional people pick s. What is this function of s? How is it found? It's found by doing an integral, an improper integral at that. The improper integral from 0 to infinity of e to the negative st times y of t dt. And this thing, if this improper integral converges, you're integrating the t out because it's an integral with respect to t, but it's got an s in there. It's got to depend on s. It is a function of s. Sometimes people call it capital Y of s. It is definitely not clear that this is a useful thing to do, okay? But it turns out it is. You may have heard of Fourier transforms as well. Is this related to Fourier transforms? Yes, it is. There are other kinds of transforms as well. Z transforms. I think there's some others. I forget what they are. These kind of transforms have applications for ordinary differential equations. They have applications for partial differential equations. They have plenty of applications in signal processing, just like Fourier series do. Pretty big, important topic in advanced engineering math. And yeah, I mentioned this, I think, before. Karen Rogers loves Laplace transforms. So if you get into Laplace transforms, it'll make her really happy. All right. What do we do with it? We take the Laplace transform of both sides of the differential equation. First of all, plug both sides of the differential equation into the Laplace transform operator. Like this. It's also kind of fun, okay? Laplace transforms are also kind of fun, kinda, if you got a taste for things like this. Okay, what do I do? I guess the right-hand side, I could actually compute it, perhaps. What does that equal? I guess I got to replace little y of t with e to the negative 5t. This is the improper integral from 0 to infinity of e to the negative st times e to the negative 5t dt. To do such an improper integral, you'd want to add the exponents, which in this case, you know, if you add these things, you get negative st minus 5t. Common factor of t could be factored out. There's also a common factor of negative 1 that could be factored out. Let's see, would that be best to do? I think so. Negative in parentheses s plus 5t. I think is probably the best way to write that. Technically speaking, I hope you remember from Calc 2, improper integrals are limits. I will go ahead and write a limit calculation here. And you should too, to get a little practice with it. Of course, sometimes we get lazy and don't write the limit sign. Is that okay? Maybe. I guess I'm not being non-committal at the moment. All right. Let the upper limit, call it b, go to infinity. There is an issue about whether the limit exists or not. It may or may not exist. Keep the limit sign there. Do the integral. With respect to t, s plus 5 is acting like a constant when you do the integral. A little bit of guesswork reveals this for an antiderivative, right there. Right, guess it. You can double check it in your mind by differentiation. Use the chain rule, s plus 5s and the negative signs cancel. Now plug in the limits of integration. You plug in t equals b and you get negative 1 over s plus 5 times e to the negative s plus 5 times b. Plug in t equals 0, e to the 0 is 1, so you're left with this, right? Careful about minus signs. Okay, now we can get a little sloppy, maybe, and say this goes to 0 as b goes to infinity, or does it? Does it go to 0?
Close enough.
Close enough. It goes to 0 if this coefficient of b really is negative. Now you see a negative sign there, but that coefficient is only going to be negative if s plus 5 itself is positive. In other words, if s is bigger than negative 5. This goes to 0 as b goes to infinity if s plus 5 is positive, which is equivalent to saying s itself is bigger than negative 5. Is s bigger than negative 5 or not? It could be. It depends what you decide s should be. That sounds kind of weird. In that case, in the case where s is bigger than negative 5, the final answer is going to be, these two negative signs make a plus sign, 1 over s plus 5. A function of s that I guess would exist as this limit if s is bigger than negative 5. It's like a function of s with this domain. Now, of course, you could plug a number less than negative 5 into this equation here, this expression. But the point is, this calculation is only valid if s is bigger than negative 5. That's the point. That makes sense? Now, we actually don't care about the domain too much. We more care about the formula, although technically speaking, the domain should be kept track of. But we mostly care about the formula, and that's what it equals. Okay, so what? That's what that equals. And it is a function of s. What happens with this? I did say L is a linear transformation. Hey, this is a linear combination. Operation preserving. Remember that? Linear transformations are operation preserving. This whole thing equals L of the first thing, dy dt, plus 4 times L of y. Right? That's operation preserving. I haven't mentioned operation preserving for 2 months or so. With matrices, you know, operation preserving meant you could write things like this. A could be a matrix, or it could be a linear transformation. I also could put scalars in there as well and pull those out. Linearity is the name I use for it, as well as other people. Okay. So what? What are we after anyway? Hey, we want to solve for little y, right? Oh, here's a bright idea. Maybe if we could solve for the Laplace transform of little y, we could figure out little y itself. Does that make sense? Maybe if we could figure out what L of y is, we could figure out y itself. We got this expression involving L of y equaling this thing. Maybe we can algebraically solve for L of y. Do some algebra. But this seems to throw a wrench into things. That's not L of y, that's L of dy dt. Well, that doesn't completely throw a wrench into things. We can deal with that. Let's do a little side calculation at the bottom of the paper here. What is L of dy dt? Well, by definition, I guess it's the improper integral from 0 to infinity of e to the negative st times already as y prime of t dt. Based on what I said a minute ago, we want to solve for L of y. It'd be nice if we could relate this to L of y. Anybody have an inkling of what to do here to relate this to L of y? Even a wild guess. What? Go ahead. Cancel out the dt? Well, I mean, the problem is that there's a y prime in there, right? Instead of a y. How do you get rid of the derivative here? Take the integral. How? You're right. You're halfway there. Yeah, integration by parts. What? I'm using u, du, dv, and v here. Our calc book that we use uses u and v prime and u prime and v. When you use integration by parts, the most common application of it is to integrate a product of two things, where one of the functions is labeled u and another one might be labeled v prime. It's the derivative of something. Oh, y prime is a derivative. And if you use this notation, you'd also want to put a dt here. I guess u should be the other thing, e to the negative st. So then you got to find du, differentiate with respect to t. And then you got to integrate to find v. I guess since dv is y prime of t dt, I guess that means v is y of t. Plus c, you can take c to be 0. Integration by parts then says do u times v, e to the negative st times y of t. It's being evaluated from 0 to infinity, minus the integral of v times du. I forgot my dt here. Negative s e to the negative st, y of t dt. Right, that's integration by parts. U times v minus the integral of v du. The v is right there. That's the same as y. What does this simplify to? It's got an infinity there. I guess it's really a limit. Okay, so now I'm being a little more sloppy than I was before. I'm not going to write the limit sign. Does this go to 0 as b goes to infinity? Yeah. If s is positive, at least you got an exponential decay. Wait a minute. Does it have to go to 0? Couldn't y of t grow really fast and make it not go to 0? It could. That is conceivable, that y of t grows so fast that as the input goes to infinity, this product doesn't necessarily go to 0, even though that's an exponential decay when s is positive. So how do you get around that? assume your way around it. Assume it doesn't go to infinity so fast to make that happen. Is that okay? For the most part. I mean, your solution function is not going to grow so fast that won't happen, at least when S is big enough. I know that's kind of hand-wavy math, but, you know, when we apply math in physics and engineering and so forth, we often do hand-wavy math. Yeah, as the input goes to infinity, if S is a large enough positive number, this will go to 0, we assume. But what about when you plug in 0? It doesn't go to 0. You get e to the 0, which is 1, times y of 0. You get y of 0. Or I should, excuse me, with a minus sign. Minus y of 0. Why a minus sign? Because I'd be subtracting it because it's the bottom there. Minus y of 0, which is the initial condition. Y of 0 is 3 for this problem. Two negatives here make a plus. I can factor out the s out of the integral. And lo and behold, that integral is the Laplace transform of y. So what we've just found here, at least assuming y of t doesn't grow too fast, is that the Laplace transform of its derivative is negative of its initial value plus s times the Laplace transform of the function itself. That's useful. Go back up here. That's what this gets replaced with. Negative y of 0 plus s times the Laplace transform of y. Which, of course, you could also write in the other order. S times the Laplace transform of y minus y of 0. And y of 0, yeah, is negative 3. So this becomes s times the Laplace transform of y minus 3. We now have an algebraic equation, an algebraic expression for the unknown Laplace transform of y that equals some specific function here, 1 over s plus 5. We can algebraically solve for L of y. We've turned calculus into algebra. That's a common feature of transforms. They turn calculus into algebra. Solve for L of y algebraically. Add 3 to both sides. Out of these two terms, factor out L of y to get L of y times in parentheses s plus 4. Then divide both sides by s plus 4. Doing that all at once would give the Laplace transform of y equaling 1 over s plus 5 plus 3, all divided by s plus 4. I added 3 to both sides. And then I divided both, after factoring out L of y, I divided both sides by s plus 4. Which can be simplified to 1 over s plus 4 times s plus 5 plus 1 or 3 over s plus 4 is one way to simplify it into the sum of two fractions. And this is the way you will want to simplify it. It could be simplified into just one fraction, but this is the best thing to do here. But this still begs a question. We're still not done. If that's the Laplace transform of the solution, what does that mean the solution is? And I'm hoping I didn't make a mistake here. Equals 3. Okay. I think this is okay, but okay, so the question is, what do we do now? I'm not going to show you all the algebraic details by hand, though you should watch the lectures to see some algebraic details and read the book. Let me hint at what to do first, and then we'll use technology to finish it. One thing you're going to want to do is take this expression and use partial fractions like you did in Calc 2 to do integrals. Solve for A and B. And then once you found A, you would want to combine it with this other one. You also want to find B. And then you do want to find Y by taking the inverse Laplace transform of both sides. If there's a Laplace transform, that's a linear transformation. Is it invertible? Does it have an inverse transformation? L inverse. Yes, it does. Oh, this sounds like it's getting worse. If this is the formula for L, what's the formula for L inverse? There is no formula for it. What? It's like doing antiderivatives. How do you do antiderivatives? You use derivatives to do antiderivatives, right? Antiderivative of cosine of t is sine of t, since the derivative of sine of t is cosine of t. Same kind of thing happens with Laplace transforms. There's no formula for L inverse. You use known facts about L to find facts about L inverse. That's what you typically have to do with inverse functions. All right, let's have Mathematica finish it for us. In Mathematica, you can do partial fractions with a part. So I'm first just doing the partial fraction calculation. There's how it works. And so in terms of A and B, what this means is A equals 1 and B equals -1. And so L of Y, if you use what I had on the paper, ends up equaling 1 over, let's see. No, A was 1. 4 over S plus 4 minus 1 over S plus 5. That's what you end up getting. So you could write that down if you want. A ends up being 4 and B ends up equaling negative. No, A is 3, but when you combine it with the other one, this is the thing we need to take the inverse Laplace transform of. Since the Laplace transform is linear, the inverse Laplace transform is linear as well. Hey, how about that? Inverse Laplace transform in Mathematica is a built-in function. What's the inverse Laplace transform of this? Let's do it without the 4. Here's the syntax. We want to take the inverse Laplace transform of 1 over S plus 4, emphasizing that for that expression, S is the variable, and we want our answer to be a function of t, is what this syntax does. E to the -4t. With the 4 there, we have a 4e to the -4t, which, lo and behold, is part of the answer. And the other one is pretty similar. Inverse Laplace transform of 1 over S plus 5 is e to the -5t. And it's got a negative sign in front of it. So that gives that part of the answer. Done. Hey, wait. Didn't we have to solve for C? The C is already solved for. Saves you a tiny bit of work. How? How is the C solved for? Because of the 3 there, y of 0, going into this. We use the initial condition when solving for the Laplace transform. And so we don't need to solve for C in the end. It gives us the unique solution at the very end without bothering to solve for C. Pretty cool. Here's how you could use the Laplace transform in Mathematica completely from the start. There's a built-in Laplace transform function as well. You could plug in the differential equation, though you'd want to do it with double equal signs. So now I'm taking the Laplace transform of both sides of the differential equation. This crazy thing here essentially represents L of y. You see it's in two spots. We can get Mathematica to solve that last output for the unknown Laplace transform. Get that. We can then take that output and substitute in y of 0 equals 3 like this. And then we can take the inverse Laplace transform of this thing, which is a disguised form of what we got, evidently, and expand it. And there's our answer again. Okay. So yes, this is more work. It's more work, but it's better for second order equations that involve discontinuous forcing functions. And there's other reasons for the Laplace transform that we won't have time to get to. I'll just point out in the reading, we only get through section 6.3 before the final exam. But chapter 6 does have more sections that we don't get to. And in particular, I know for the purposes of engineering, not because I'm an expert in engineering, but if you do work through section 6.5 on something called convolutions, and 6.6, the qualitative theory of Laplace transforms, it's definitely relevant for engineering problems. Okay, I'm not saying it's easy, but it might be worth reading. Well, maybe not over Christmas, but maybe before math methods or something like that. Reading those couple sections is a pretty useful thing. I know in particular, especially with these black box ideas, are relevant for engineering problems.